We're glad today that we're hosting Iman Hmedoush, which is currently a third-year PhD researcher at INRIA Lab. She has took her Bachelor of Engineering from Tishrin University, and she has made her Master in Research at Supalak. And today she will be talking about reinforcement learning applied to the Internet of Things and especially to the wireless technologies. Hello, Iman.
Hey, Natasha. How are you?
I'm fine. How are you?
Awesome.
So, okay, I guess, Iman, you have to share your screen with us. Okay. Okay. So,
is it fine?
Yes, now it's shared.
Okay, but I guess I can hear the echo of my voice. I don't know, maybe some of you.
I guess the voice is good.
Okay, great.
Okay.
So can I start?
Yes, for sure.
Okay. So hello again, everyone. My name is Iman Hmedoush, and I am a third-year PhD student at INRIA. So I'm doing this PhD with INRIA and also with a collaboration with Nokia Bell Labs. Today, I'm going to explain to you one of my conference papers, which was accepted in Machine Learning for Networking conference in Paris 2020. So the paper is titled as a Regret Minimization Approach to Frameless Irregular Repetition Slotted Aloha. I did it with my two supervisors, Cedric Achi and Paul Molteler. So in this presentation, I'm going to give a small introduction about the main topic that I'm working on, which is IoT networks. Then I'm going to explain to you the main protocol that we work on, which is IRSA. Then I'm going to give you an overview about the system model. Then I'm going to explain the learning algorithm that we followed. So last but not least, the simulation results. I'm going to show you the main simulation results we had. And finally, I'm going to conclude the idea of the work. So as you may all know, IoT network is still not applied to our life. But when people listen about an IoT network, they just think about smart homes, like I have a fridge or I have an oven that I can control from my work or from outside. But actually, IoT applications are wider than that, and they are more important than that. IoT network represents a huge influx of data from different devices that they share the same radio spectrum. And the IoT applications are enormous, including smart homes, medical and healthcare applications, building automation, automated cars, etc. So it has enormous applications, and it will come a necessity more than just a side advantage that it will come to our life. So as the applications of IoT network are numerous or wide, IoT network has or still has some main challenges. That's why it's still not wide existing in the world. The main challenges are the power management. We need to minimize the consumption of the power for all the devices. The device management, including the security, including how are we going to connect million devices at the same time, and such that we ensure that they are connected, there's no problem. So my problem here, or the problem that I'm trying to solve, is the connectivity in IoT networks. So I'm working how we develop protocols such that we guarantee the connectivity of millions of devices at the same time.
So your role is about developing these protocols to guarantee this the well connectivity in the IoT networks, right?
Exactly. So as you know here, now we have millions or billions of devices that they are connected, but after 10 years or 15 years, when more objects, the objects will need to talk with each other. So we will have this number of connected objects will multiply by 2 or 3 or 4.
Yes, exactly.
the protocols that we have now, they will not work for this enormous number of objects. So we need from now to think, either we start new protocols from the zero, from the base,
exactly.
or we develop the protocols that we have in order to fit the needs of an IoT network. So that's why here we have two suggested solutions in the next slide. Okay. So I'm showing two solutions. We're following one of them. The first solution is to use the non-orthogonal multiple access schemes, which are used in 5G now. We have NOMA code domain NOMA, or power domain NOMA. But here we are using the alternate, or studying the alternate solution, which is the coded slotted Aloha family, which I'm going to explain. So you may listen about Aloha. Aloha is a very old connection protocol. So Aloha is just a basic protocol of connection to the internet. When you have a packet, just send it in the network. And if your packet is collided with a packet of another user, you will lose the packet and you need to resend the packet again. So after Aloha, a new developed version, which is slotted Aloha, has appeared. So in slotted Aloha, the difference is that we divided the time into slots. So we minimized the collision period into the slot time. So now you send the packet whenever you have a packet, but you are just colliding with other users into a slot period. So if you collide, you need to resend your packet. Next, a new version in 2007 appeared, which is contention resolution diversity slotted Aloha. In this version, you send your packet twice to increase your chances that you can be decoded and you are not going to collide with the packets of other users. And then here, the throughput was maximized into 0.55, while in the previous version in slotted Aloha, it was 0.37. So just for repeating the packet twice, we increased the throughput a little bit. So the last version of this family, which has appeared, which is the focus now of the researchers in IoT protocols, is the irregular repetition slotted Aloha. In this protocol, you are allowed to repeat your packet D times. This D can vary from 0, 1, 2, till capital D. It's a maximum number of repetition. You repeat the packet according to a probability distribution, but here we exploit a new feature from the physical layer, which is successive interference cancellation, which is also used in 5G now, which I'm going to explain to you in details later. So here the throughput, the maximum achieved throughput synthetically is 1 packet per slot. It means that you don't lose any packet. At each time slot, you have a retrieved packet from one user.
Iman, will this alter the power management?
Sorry?
Will this change the power management? So by sending the replicas?
Yes, it's a nice question. Of course, here I'm not going to change the power of the packets. The users are sending the packets in the same power, and the user is sending all the replicas in the same power. Mm-hmm. But I did different research work about changing the power of different users in the same class. For example, we classify the users into classes. Each class uses a different transmission power. There are multiple research works about changing the power of different replicas. It means that if you want to repeat your packet 3 times, you send in 3 different powers, and they are studying what will happen.
Okay.
So for this presentation, I'm going just to keep the packets at the same transmission power. So the idea of the protocol is that each packet is transmitted L times, as I said, according to a probability distribution, and then we use a SIC-based receiver to retrieve the collision. So here in this example, okay, let me explain. Here, for example, I'm just putting a part of a random access frame where we can see that user V, for example, is sending, his packet 3 times, while, for example, user D is sending his packet twice, user C is sending his packet twice, user B is sending 3 times, user A is sending once. So it's really up to a probability distribution. So now the main feature that SIC relies on is the successive interference cancellation. So how successive interference cancellation works? First, while all the packets arrive to the receiver starts by sending the packet which hasn't been collided with any other packet. So here in this example, packet 3 is alone. It's not colliding with any other packets. So we have advanced receiver that they can, of course, decode this packet. And then this packet will have information about where its twin or where its replicas are in the radio access frame. So this packet will have some information that my twin or my replica is on slot 2. So the receiver will go to slot 2 and it will retrieve this packet. It will just extract it from the collision from the packet 2. So the idea here is that we have advanced receivers in the physical layer that they can, if you have 2 signals or more than 2 signals that they are colliding the same time, you can extract these collisions. Just you need to reconstruct the packet. Here we reconstruct the packet on slot 3, and then you just do it's like 2 minus 1 equal 1. So you will get the packet that you already decoded. So here the receiver will retrieve the packet of user 3, and then we will have packet 2, which is now alone on slot 2, so it could be decoded, and then it could be retrieved or removed from slot 1. So we have packet 1 now alone. We remove it from where it is on the radio access frame. We have packet 6. Then we arrive, sometimes either we decode all the packets on the radio access frame, which is really the best case, or we still have some collisions that they couldn't be retrieved, which is the case of the stopping set. The stopping set is where 2 users are sending, for example, here 2 packets at the same 2 times slots. So here you cannot retrieve any one of them, and you cannot extract any one of them. So we cannot retrieve the packets of user 4 and user 5. Okay, so in our model here, we considered 2 different classes of users, class C0, class C1. Why we consider 2 different classes? Because we wanted to give some priority to some classes. So class C0 will have more priority than class C1. We have the same number of users in each class. And we consider that the number of active users is determined by a Poisson arrival rate.
Iman, what do we mean by more priority? Like
Yes. So, you know, as in IoT applications, you have some sensitive data like medical data, for example. So you need sometimes to reserve some slots or to reserve a higher throughput or a higher, lower latency for some applications. So that's why we need in some studies to consider the priority. That's why we told ourselves, while we are classifying users, let's give a class more priority than the other class and study what's going to happen. And of course, studying the priority is the much difficult way, because the parameter of priority, when you put it to 0, you don't give any priority and you go to the basic case. But you have a priority, it's the much complicated case which needed to be studied.
Okay.
Okay. So the idea is that we used, of course, here I needed to mention that we used the frameless IRSA. It means, of course, the protocol could be framed. It means that we consider frames of slot or frameless. Here we consider the frameless because it was easier for the learning algorithm. So here we consider two things. The contention round, which is, as we have frameless, we don't consider frames, but we need still to group the slots into some kind of notation just to facilitate the learning process. So we considered something which is called a contention round, which is the replacement of the frame. When you have frameless protocol, you have a contention round, which is a large set of slots that has always a fixed size of m slots. And we also considered virtual frame. What is the virtual frame? Whenever you are, as an IoT user, you want to access the network, so you are directly associated to a virtual frame. So it's at a number of slots that they are reserved to you in order to, not reserved, but you are just allowed to send your packets inside this virtual frame. So here, for example, as you see, user A is sending his packets only within the period of the virtual frame in red. User B is doing the same. Of course, you can, here we can have different collisions from different users in the virtual frame. So like user B, C, and D, or user C and D. So users from different virtual frames, of course, can collide. And here the SIG will work. So in the studies or in the related work of irregular repetition slotted Aloha, the goal of all these studies is to maximize a certain metric of the system. Either it's the throughput or the maximum achievable load, or to minimize the latency or to minimize the packet loss rate. So in whatever paper you will see about irregular repetition slotted Aloha, you will find an optimization problem, because here we are optimizing a protocol. So we're optimizing a metric of this protocol. Of course, we need to respect that we have a probability distribution. So two main conditions that they will be that each coefficient will be between 0 and 1, and the sum of the coefficients will be, of course, equal to 1. So in our problem, as we have two classes of users, they have priority. So our goal was to optimize the weighted throughput of these both classes according to some conditions. So here, why we took the weighted throughput of both classes. Of course, you know, in learning, users or in general, users can do selfishly, can behave in a selfish way, or can behave in a cooperative way. Here, we wanted the users to behave in a cooperative way. So we wanted to maximize the weighted throughput of both of them. So each class will not only optimize its throughput, but it will optimize the other class throughput, depends on the factor of priority. So alpha 0 is the priority of class C0, and alpha 1 is the priority of the class C1. So it's they are just weights to adjust the priority.
Because they are cooperating together.
Exactly, or we can say we can make them cooperating, and we can make them competing. Depends really on the priority. So this is what we will see later.
Okay.
Okay. So as we have many agents in IoT networks, I can say millions of agents. So we consider our system as a multi-agent system. We need to consider where we are in the learning. Then we consider that the base station is sending a feedback to each agent or to each user about the instantaneous load on the network. It means that when I am a user, an IoT user, and I enter the network, I receive from the base station an estimation about how many number of users estimated again could be online with me or could be connected with me to the network. So this information is important because the number of repetition, the number of degree repetition, or the degree of repetition that I will use is so important in this case if I know the loads, because if the network is overloaded, I will not repeat 10 times, but if the network is low loaded, I can repeat 10 times and I can increase my chance. So that's why we consider this estimation. So considering this estimation will classify our system into a multi-agent and a partial and has a partially observable information from the base station, which is the load. So it's important to understand the basics of the system in order to know which learning algorithm we need to use. So I can conclude now that the system is multi-agent with partial observability. So we saw in literature what people are using as a learning algorithm for such systems. We saw that multi-agent reinforcement learning approaches are the most popular and the most effective for these kind of problems. So we searched into many books and many references about reinforcement learning, multi-agent reinforcement learning for networking, and we saw that we can use regret minimization algorithm. We tried many algorithms before, but it's a very hard problem to solve. So it's not guaranteed that you try an algorithm and it works. So finally, regret minimization gave us a good performance. Okay, so here, as you know, in each learning algorithm, we have the basic vocabulary, state, action, reward, etc. So here I will just tell you what is the basic vocabulary of our learning algorithm. So the state, as I said, is the estimated load from the base station. The action is how many number of packets how many number of times I'm going to repeat my packet. So it's the number of repetitions. So the reward is how many number of decoded agents in both the classes. And it will come from the environment. So I will use this information about how many number of decoded agents in each class I achieved, and then I will use this information to compute the reward. I will show you that later. And then we have some tables called W tables. These W tables are really the basics of regret minimization. And in these tables, we will evaluate each action by putting a weight to each action. And then based on the weight of the action, I will compute the probability to use this action later in the next round, on the next play.
Iman, sorry, but in the previous slide, so it's based on the number of decoded agents in both classes. We will choose in the next step what is the number of repetitions.
Exactly.
Okay, so this way it will learn what is the best. Okay.
Exactly. So it will take a decision how many number of times it will repeat, and then we will see how many number. So of course, the number of repetitions will make collisions. So based on the collisions, you will decode or not decode. So the number of decoded packets give you information about how much your action was useful or was good or not. So this will be here in this slide, I guess.
Iman,
so
here. Question. Yeah. The reward function will also be weighted by the priority of the class?
Yes, exactly. I will show you that later. Okay. So here I will just explain in details by a small example about how the learning will work. So here we have two classes, C0 and C1. So I will remind you that C0 has a higher priority than the class C1. So here we have two classes, A from class C0, B from class C1 in green. Okay, both users are connected at the same time, at time t, so they are associated to a virtual frame. So here they will send their packets just within the virtual frame. So as they are connected, they will receive the estimation about how about the load, how many users are connected to the network. So based on this estimation, they will decide the state. What is the estimated load? This is the state. And then based on the state, they will select the degree. Okay, so this is the initial step. Of course, we initialize the W tables or any learning algorithm before, and then we adapt the initial value by the learning. So the degree is selected. So they will send the packet. Here we see that user A or agent A selected action 4. It repeats its packet 4 times. User B repeats its packet 3 times. So what's going to happen is that in the environment, which is the base station, there will be the decoding, okay? So the base station will decode the packets, and then it will send the feedback to both users, how many number of agents are decoded. And then the users will compute the reward based on this feedback, and they will update the probability to use this action by the learning algorithm. So it's just how the learning happens in general, but we will go into
Is there something who's changing the location of the virtual frame? For example, if we want to start the virtual frame of A from the second slot to the last slot?
You cannot, because when you are connected, or when you are ready to send a packet, you are associated to a virtual frame.
So this is a constraint, not
exactly. It's a constraint. You cannot change, because otherwise it's another kind of problem to select the slots or to shift the virtual frame.
Okay.
So it's an interesting question, because in this type of protocol, we don't also we don't only optimize the degree. We optimize sometimes the location where we send the collision, the replicas, which is really an important subject also.
Okay.
But doing both of them at the same time is so difficult. We're trying to do that now with a Lebanese researcher. So the algorithm, the regret minimization algorithm, is based on weights for each action. And based on these weights, we use a probability, or we compute a probability to use this action later. So just briefly, I will not complicate things. I will just explain you the algorithm briefly. Each agent select an action according to some probability, which is initialized at first. And then it will compute the reward of this selected actions, which is Ri. And then it will compute an optimal reward of the optimal action that this agent could have played. So of course, we take all decisions in our life, but we know that sometimes we regret a decision that we took. For example, I did a PhD. Okay, I don't regret, but let's say I regret doing a PhD. What was the optimal decision that I will do when I finished my master? To go to work, to go back to my country, whatever. So of course, sometimes we have an optimal action which we don't know. we don't know how to take it at the same moment, but we know that there was an optimal action. Here it's the same. The user is taking an action, but sometimes there was an optimal action that he could take, and he could maybe achieve a zero throughput. So the regret or the loss is the difference between the optimal reward, which is related to the optimal action that it could has been taken, and the real reward, which is the reward of the action that it has really taken. So that's why the algorithm is called the regret minimization. We need to minimize the difference between the reward of the action that we take and the optimal action. It means that we need to approach towards the optimal action.
I have a question. I don't know if it's already in the formula or not, but the regret is something that the agent itself has to figure it out, or it's coming from the environment?
It's coming, it's a nice question. It's coming from the environment because it's a centralized learning.
Okay.
I maybe missed this point, but it's a centralized learning. So the learning is done at the base station. So the agent is given the information about how many number of users have been decoded, which is the reward. So the reward is not really, it's just computed by the agent, but it's not really figured out by the agent because it's the base station which does the decoding and which computes really the basic of the reward.
No, I mean that, for example, isn't more powerful if the agent can know here if he has to regret something or not? Because
yes, if the agent knows, it's much powerful because it can behave faster. But the issue is that when you are if you want to do distributed learning with millions of agents, it will be very hard to converge. So the solution here is to do a centralized learning because it's easier, and also we did it offline. It means that the agents are not learning offline. We do it offline, and then the results, the optimal distributions that we will get from learning, we give them to the agents and they use them online.
Okay.
Okay. Yes, so after that, the loss is the difference between the optimal reward and the actual reward. We use the loss in order to evaluate a weight or to consider a weight for each action. And then this weight is used to compute the probability to use the action later in the next round. So the probability to use each action will be the weight of this action divided by the sum of the weights of all other possible actions. Okay, so here the reward explanation. The reward of the class C0, which has the higher priority, is we consider this reward as the throughput or the number of decoded users inside this class, because it has a priority. But the reward of the class 1, which has a lower priority, it's alpha times the number of packets, the number of agents that they have been decoded from this class, plus 1 minus alpha times the number of packets or number of users that they were decoded from the class C0, which has a higher priority. So here we really see the priority effect in the reward. You see, so it's just, we have 1 minus alpha of the packet loss rate of the other class, of the competing class. So here we see that we gave the priority of class C0 and we forced the class C1 to work such that it optimizes its packet, its throughput, but it's also optimizing at the same time the packet, the throughput, or it minimizes the packet loss rate of the other class, which has higher priority. Okay, so here just a small remark about how we did the reward computation, because the reward is related to the optimal action and the actual action. So we have optimal reward and the real reward, let's say. So we did a main simulation where one agent is taking an action, like for example, agent A is taking action 3, agent B on the line is taking action 2, agent C is taking action 1, etc. Then we did alternative simulations, like we fixed what all the agents are playing, and then we changed the what could the agent A play. So for example, the agent A played action 3, but it could play action 1, action 2, action 4, action 6. So we make this agent changing its action, and then we computed the reward that it could happen if this agent took this action or that action. So of course, this process is costly for time and for computation.
Also, for example, if agent 1 have taken some action, but you also have to see what agent B have taken at the same time, because it's like.
So here we fixed what agent B has taken, but then you see alternate simulation of B. So we also changed we fixed, for example, 3 action or user A is taking action 3, and then we fixed the others. We changed for user A, and then we fixed for user A, and again changed for user B and user C. So it was really hard work. It was really hard in time and in computation, but in order to minimize the possibilities, we minimized the number of degrees that users could select. So
sorry, Iman, but also it's related to the computation for the number D. For example, if it's continuous or discrete, and in our case it's discrete, but it might be a lot bigger than the number of Ds that you have took, right? So if we increase the number of D, so this solution might be a bit like tough.
Okay, I didn't understand the last sentence. I haven't heard.
Yes, so the solution, isn't the solution related a bit to the number of repetitions you are considering?
For sure, yes.
So it will be more complex in this case if we have an increased number of repetitions.
Exactly, that's why we limited the number of repetitions.
Okay.
That's why we haven't gone to 15 or 20 for sure, because this will complicate the process. We limited the number of repetitions, and also looking at the previous works, people are not using high degrees of repetitions, like they're not using 15 or 20 degrees. So this is not really logical.
Okay.
So that's why this helped us a little bit, but still the simulations took 3 or 4 days.
Oh.
Yeah, this was really complicated.
What is the order of the number of agents that you are using in simulation?
What do you mean by the order?
Approximately how many agents?
Approximately how many agents? I guess we went to 500, something like that.
Okay.
So here this slide is a conclusion of what I said. We have a learning phase. I just here put some parameters about the learning. So we had 5,000 episodes. The learning rate was 0.04. Of course, the learning rate took from us some time to adopt because it's an important parameter. The load is valid between 0.1 till 1.2. This is the W table, the shape of the W table. Then we have the probability to use each action, and then we go to an evaluation phase. So we will get some optimal distributions, and then we'll evaluate if these distributions are really good. We will compare them with other optimized distributions with other different ways. So let's go to the results part. So here in this slide, I'm showing to you the achieved throughput for both classes. So the class which has the higher priority is the class in blue, C0, and the other class with low priority is in orange. So the ideal throughput that all researchers now are searching to achieve is the one in red, which is the throughput is equal to the load. It means how many number of agents you have in the network, you need to decode all of them. So your throughput will be equal to the load. So that's why you see a straight line, because they are equal, the throughput equal to the load. Of course, this one is asymptotically achieved, but when you go to simulation or when you do studies, till now it's very hard to achieve. So here we see that class C0 in both figures on top, we are using actions with 0. So the action 0 is inside these classes. So as we have priority and as class C1 is working for class C0, let's say. So he's preferring to send the with action 0. It means he's not sending. So when you select action 0, you send no packet. So here we see that the throughput in orange for class C1 is lower, much lower than the throughput of the class C1 in blue. So there is a gap between both of them. While when we change the set of actions that they were allowed for both users in the two figures below, you see that the throughput of both the classes is really close. You don't see really the gap. Why? Because here we have the set of actions are 1 through and 6. Okay, so one is when the class C1 is forced to send, especially for high loads, it will send with the lowest action. It will not repeat too much, just to make the space for, or to let the network for the class C0. So it will select the lowest action, which is 1. So 1 will allow him at least to have a considerable throughput, let's say. So here really we see the importance of choosing the actions, the action set, the importance of that, or the impact of that on the network performance.
Okay.
So then here we compared with a well-known researcher who I can say the godfather of this protocol, which is Gianluigi Liva. So he studied this protocol and he optimized it using an optimizer or using optimization, solving an optimization problem. So we took an example of his distribution, and we compared with his distribution in blue. Of course, his distribution in blue and our distributions are in yellow and green. So we see that the distribution, or the throughput, the throughput achieved by our distribution in yellow, for example, at least for class C0, is either higher than the optimized distribution by the researcher, or at least it's considerable sometimes, especially in the lower figures. So here, the goal of this comparison is to see, is the learning working better than the optimization, the regular optimization? And it's of course important to compare our approach with the approaches of the other researchers that they are working on the same topic. So here we see that we have really either a better performance or a very close performance. We're very happy when we see.
For the blue curve, is this the state-of-the-art performance?
Exactly, it's the state of the art. So you see in the both below figures, it's very close. And this, I need to say that this performance is asymptotic. Asymptotic, it means that when the frame length is going to infinity, which we don't have in reality. So if you are really close to the asymptotic performance, you are really performing good. So that's why we were happy for that. And also sometimes for some loads, the algorithm is working much better, like in the upper figures. For class at least C0. For class C1, of course, no, because he has a lower probability.
Mm-hmm. And in the figures C and D, we realized that we are taking the special actions 2, 3, 5, and that's why also it's getting better and better.
Exactly, and that's why also both you can see the green and the yellow are very close to each other, because the class C1 is forced to send with 2 degrees, or yes, in both figures, while in the upper figures we have action 0 and action 1. So that's why you see the gap between the at least in the figure number A, you see a gap between the yellow and the green, because we have action 0. So the class C1 prefers not to send.
Okay.
So you see the gap, while in the others, while he has a chance to send, his throughput is enhanced.
Good.
Okay, so here we see the learning curves. It's just to see when the learning or when the algorithm starts to learn. Of course, it takes time because the action space is huge. It's not really the action space, because the action space is the probability to use each degree, and of course probability between 0 and 1, we are varying the probability between 0 and 1, but we are taking really a small step. So that's why I can say that the action space is huge and the problem is difficult. So that's why I can say that the learning here took like 3,500 episodes in order to converge. Okay, so to conclude the work, the importance of this work is to show that we have some solutions to work for the problem of connectivity in IoT networks, because it's really a major problem that it needs to be solved. We don't need to go and design protocols from zero. We just need to go and to adapt the existing protocols such that they fit the needs of an IoT network. We suggested this irregular repetition slotted Aloha with its frame-based version. We proposed IRSA RM, which is a reinforcement learning approach based on regret minimization to optimize the strategy of regular repetition slotted Aloha. So the learning is performed offline, as I said, and we were learning the main protocol parameter, which is the probability distribution. After the learning phase, this learned distribution will be used in the network, and simulation results showed us a great performance of this protocol when it is learned with regret minimization, and also it is compared with some external optimized distributions by other works. So thank you very much for your listening to the presentation, and if you have any questions, I'm ready for that.
I guess it's a really nice application based on the comparison that you did with the, as you mentioned, the godfather of the field. I'm really glad that we're now seeing the innovations of reinforcement learning in the field of IoT. So please, guys, if you have any questions to ask to Iman, please let us know.
Thank you for the presentation. Just I want to make sure, like you told us that it took like around 3 to 4 days the learning algorithm to be trained.
Sorry, I cannot hear you very well. The voice is very.
The voice. I'm not sure. Okay, so do you hear me now or not?
I don't think it's much better.
Okay, so.
Natasha, Lina, can you hear Chadi?
I can hear him, but it's not a very good voice.
Yeah.
There's a bit of noise in the voice.
Okay, so.
There's an echo, I guess, behind your voice.
Yes. But you can ask, and I can repeat the question.
Yeah. So you can. It's okay. So just just I want to make sure, like, how much time does it take, like, to train like a learning algorithm?
I understand.
Yeah.
How much time I need to
So I guess you told us like 3 to 4 days.
Yes, for some simulations, yes, it took 3 to 4 days because you have like 500 agents. You have a frameless protocol, and also you have a set of actions which is not small. And also the regret minimization itself, it takes time. And we do many processes inside. We compute the reward, we compute optimal reward, and we compute the actual reward. And for me, actually, the most consumed time was for the to compute the optimal action, because you need to try really do many simulations and to change the action and play all the action at the same time that they could be played. So it took like 3 or 4 days for some simulations to be finished.
I see. And just like a simple question, just like what courses or book like do you suggest like to learn reinforcement learning? Because like now it's applied everywhere, even in an LP. So just like what
sure,
what books like someone can read, or like courses like to know a bit about the field.
Yes, honestly, I followed a well-known book which I love for reinforcement learning, but honestly, I never memorized a title of a book.
I guess
Sutton and
I guess all of you know it, but it's really even I have a real version of it, but I don't know where
it's from MIT Press, I guess.
Okay, let me. I can search for that, and I can provide you I can provide for you the information. Okay.
I guess an introduction to MIT. I remember something like that was very important in the field.
It's not really from the MIT. But it's really a very well-known book where you can really find all the algorithms of reinforcement learning, the basic ones, of course, not the modified one, because now researchers are taking the basic algorithms and they just adapt them to their problems.
Okay.
So do you see folder books?
Is it from Richard Sutton?
I guess Richard Sutton, yes. I guess you got it, Lina.
It's called Reinforcement Learning and Introduction.
An introduction, exactly. It's this one. Yeah. For me, I followed this one. Honestly, I saw when I read most of the articles, I saw that they refer to this book a lot, and I saw that it's very clear. It has many like many explanation about each algorithm, and it has all the variants of the same algorithm. So for me, it was good, at least at the start. But I have like a list of books and a list of videos. If you want, if you are interested, I can.
It would be great if you can like share with us.
Yeah, of course. So I need to see the folder, but I am not seeing the folder here. But I will see the folder, and of course, I have some videos that my supervisor provided me. They're really good for reinforcement learning and for deep learning as well.
It's very nice.
I think also there is the lectures from David Silver. You can find it on YouTube. It's about reinforcement learning.
From DeepMind, I guess.
Yes.
And there's also a series of courses related to deep learning, and they have made one episode regarding reinforcement learning by the MIT University. So we can share it also with the episode that we will publish.
Okay. Okay. So here I have some books, but I don't think they're learning here inside the folder, the learning book. Here there are books for coding theory and this stuff.
We can provide the title later, as we have mentioned. Iman, I have a question regarding the simulation.
Yeah.
You have mentioned that you have applied the algorithm on a series of simulations that you have made.
Yeah.
Will the case be different if you are applying the algorithm on real case scenarios, and if you have trained the algorithm on simulation? Will it be different if you apply it on a real case?
Of course, it will be much different. Why? Because in a real case, you have more agents than that. So in an IoT network, you have, I guess, more than 500 users. Because also you compute the reward considering that the SIC receiver will not fail. You consider that there is no fail in the receiver, there is no noise. You work in really here in research work in good conditions, in ideal conditions, let's say.
Yes.
So of course, you don't consider that because we also have a problem in the SIC receiver that when you decode a packet and you want to extract the signal physically, you create a noise, you left some energy, and this energy just will be accumulated slot by slot, and this will not let the decoding process successful 100%. So here we don't consider that. We don't consider that we have a high number of users as an IoT network, as a real scenario. We don't also consider, we haven't took all the alternatives for sure. We took like the major of them, but not all of them, because otherwise the simulation will take forever. So of course it will be different, not really different, but there will be a difference. I cannot guarantee that it will work successfully 100%.
Yes.
But Iman, these solutions are already deployed in some way, no?
What do you mean these solutions?
Like I don't what is the name of this solution? Yeah, the first.
Yes, the protocol is not really used. It's now a candidate to be worked.
Okay, so it's not deployed yet.
No, it's not deployed yet because it's really a strong candidate to be working for IoT networks in the next, let's say, 5-10 years. I expect 10 years. It's not really deployed as to my knowledge, but there are like hundreds or maybe thousands now of research topics on this protocol.
Okay, nice.
So it's still in the labs. It's not yet in the.
Because IoT is still, I guess we can say, in the labs. It's still not really deployed in the real network or in the real life. So
We're still waiting for the 5G to be deployed so that we can.
Yeah, but I was confused because you said before that you are working on how to adapt the already existing protocols for IoT. So this protocol does exist before or no?
Yeah, it exists because okay, let's be clear. It exists for sure as a topic. So it just exists in 2011. I don't know if it has been really tested in the lab. I guess it has been tested, but at least up to my knowledge, it's not really let's say officially used by some companies or by some by an official legalization, let's say.
Okay, and it was developed at the first place for what purpose?
It was developed for just not for IoT. The author it hasn't mentioned IoT in his work, but it was developed to enhance the random access method, because anyway, it's IoT. It's under the title under random access. You don't control the access of the user, so it was to enhance the random access method.
Okay, nice.
Very nice. And the main novelty of Iman's work is that she has took this protocol. She didn't make anything from scratch, and she has made some advancements on this protocol. So with the regret minimization algorithm.
Exactly.
I also have one question. You mentioned that you have took the frameless version of this protocol. Will the results change like radically if we took the version with like the frame version?
I don't think so, but it was just a kind. We took it for the reason of simplicity for the learning, but because just for the computation of the reward, because that when you want to compute the reward, you cannot guarantee that you cannot compute the reward within the virtual frame. Why? Because your packet will be collided with users from other virtual frame, and you need to wait up the virtual frame, for example, of user B is finished here. So you know if user B is decoded to extract it and to decode user A. So this was really like a hardship in the work. Why? Because you cannot restrict yourself by a frame. So that's why we left everything open. We created the concept of virtual frame just to for the decoding and for the successive interference cancellation process.
Okay.
I don't know if this was clear.
Yeah, it is clear.
I have also one question. We know now that in reinforcement learning, there's this very cool approach of having a very deep network and getting very better results. So here, are you applying deep reinforcement learning or just regular
reinforcement learning? Now I am about to apply deep learning. We're going to work on this protocol also with the idea of classes and priority, but with also selecting where to send the packets, not also how many number of times I need to select to send the packet, but also where to send the packet, which is the hardest problem. We need to control both of them. So here you need a deep reinforcement learning.
Okay.
Best of luck. All right, guys. So we're glad that we have made this episode about reinforcement learning for the Internet of Things. Thank you, Iman, for this presentation, and thank you, everyone, for discussing Iman's presentation.
Thank you, Iman.
Thank you, Iman.
Thank you, everyone, for listening. Thank you, Chadi. Thank you, Lina.